we've seen the concept of differentials in Calc 1. The idea was a differential was if there's a small change in an x, how does that affect the y? So in Calc 1, we solved this form for the differential that dy was the derivative times the small change in x. So now, of course, remember this was given that y was a function of x, of course. So if you did a small change in y, there was this factor that told us how much, or a small change in x, this factor here told us how much the y changed because of it. Now, how do we do that instead of now if we have z is some function of x and y? So now we're extending the idea a little bit farther. And a lot of times, a lot of books will call this the total derivative. I think that's not a really good name. But really, we're just taking a look at what the differential would look like. Well, the same concept is going to just be expanded over. So a small change in z will come by if what? Well, if we do the same look, we're going to have to look at how this thing changes when we move in the x direction. So that's going to be the derivative in the x direction. So this is how much the z is going to change when we just move solely in the x direction. It's the derivative with respect to x. So that's almost exactly what this is. However, since z also has another independent variable, we have to say how much does it affect it when we move in the y direction also. All right, so you see our differential becomes slightly more complicated because we had to look at how much motion in other directions affects the final product. Now, if we had something, I'm not going to write this out, if we had dw, and let's say this was a function of x, y, and z, well, we'd have the same idea, but we'd have an f sub z dz. So you just tack on every direction that you can move in, it's differential. All right, let's actually look at a Calc 1 problem before we expand this to a Calc 3 problem and see that it really is the same exact concept. So this is more of Calc 1. Since I know a lot of people that take a course like this are generally going to be engineers, let's put this in terms of something that would be a real life problem. Let's say that you're building an engine, like a jet engine, and you need to buy some ball bearings for this jet engine. So ball bearings with a diameter of 2 millimeters. Okay, so that's what you need. You need a whole bunch of ball bearings that have a diameter of 2 millimeters. However, one of the problems we have in the real world is something called the measurement problem. We can never measure anything exactly, no matter how hard we try, because no matter what ruler that you use, there's always error in that measuring device, whatever ruler it happens to be. The same thing when we're building stuff, when we're making things, when we want a specific size, there's going to be some error built into that. So let's say you needed these ball bearings to be 2 millimeters in diameter, and you go to the factory, machine that makes them has a tolerance, that might not be spelled right, of plus or minus 0.02 millimeters. So the machine that makes it in the diameter. Okay, so this thing can make ball bearings that are really close to 2 millimeters in diameter, but it could be off by as much as 2 millimeters too big and 2 millimeters, 2/100ths of a millimeter too big and 2/100ths of a millimeter too small. So the question is that going to mess up your engine? Do you need to be more precise in that? Do you need to find somebody that can make a better one? Well, first off, let's see if we can determine how bad this would be. Ball bearings work off of generally all being the same size, and one good measurement for the size of a sphere would be its volume. Now, I know the volume of a sphere, excuse me, is 4/3 pi r cubed. So that's what it should be. But we're going to have this small change in the radius based off of this measurement. So the radius isn't going to be exactly 1 millimeter. It'll be 1 because half of that. It's not going to be exactly 1 millimeter. It's going to be off by a little bit. So how much is that little bit of off possibility going to throw off the final size of the ball? Well, what we're looking for here is the derivative of this in differential form. So a small change in volume will be 4 pi r squared times the change in the radius. So in this case, let's plug in what we know. I'm going to move this up here. So dV would be 4 pi. Now the radius would be 1 because we wanted the diameter to be 2. And dr is going to be plus or minus. Now I told you this was the area measuring the diameter, so we could possibly assume that half of that would be measuring the radius. So let's say that it would be plus or minus 0.01. Now first off, when you put the plus or minus into these problems, you're always going to want to pick the pluses and minuses that either maximizes or minimizes the final product. Kind of like if you had something minus something else plus something else. To make this as big as possible when you had plus or minuses here, one of the easiest way to see this is if you picked a plus, a minus, and then a plus, it would make them all the same sign, and that would make it as big or small as possible, or a negative and a positive and a negative. So you don't want to pick the one that maximizes it, so you can kind of look at the worst case scenario. Now in this case, since we only have one term up there, I'm just going to leave the plus or minus as a plus or minus. So this ends up being 0.045. Well, pi is about 3, right? So just off the top of my head, this is approximately 3 times 0.4 would be 0.12. Is that a lot? I don't know. Now remember, our units are millimeters, and since its volume would be cubed. Is that going to greatly change the size of our ball bearing? Unfortunately, it's really hard to tell with something like this because that's just a blank number with no perspective on it. Is 0.12 millimeters cubed a lot? Well, compared to the volume of, say, an Olympic swimming pool, no, it's tiny. But compared to the size of a blood cell, it's huge. So instead of looking at this number as a raw number, what we generally look at is called relative error. Basically, how does that compare to the size of the thing that we're looking at? So you've probably seen this in your science classes. And it's always the part over the whole kind of thing. So our part here, what are we looking at, would be dV over what the volume should be. So we're going to compare the volume, the possible biggest error in the volume, by the way, it's plus or minus right there, in the volume, compared to what the actual volume of it is. That way we can see if it's big compared to what its actual size is. So here we get plus or minus 0.04 pi divided by what's the volume supposed to be? Well, this would be our volume, and the diameter is supposed to be 2 millimeters. So this would be 4/3 pi times 2 cubed. All right, so doing a little bit of arithmetic here, the pi's are going to reduce. Those 4's will reduce, so that's plus or minus. What's that going to give me? That's 8 times 3 would be 24. So, oops, sorry. I was about to write a unit there. All right, so is that a lot? Well, think about this in terms of percentages. Got my decimal in the right place? Yeah. All right, so think about this in terms of percentage. That means this could be off by as much as plus or minus 24% of the whole. Seems awful big. I feel like I made an arithmetic mistake. Oh, I did. Sorry. This is wrong. That's an arithmetic mistake. Let me go ahead and write this out for you. So we get plus or minus 0.04 pi over, that's 4 pi times 8. This is going to be kind of an ugly number. Should have made that a 1. All right, so of course the pi's are going to cancel, and we end up with here dV over V. This ends up being plus or minus 0.03 divided by 8. 1, 2, 3. So dV over V is approximately plus or minus, let's see, 30 divided by 8 is, let's say, ish. I'm just guessing there, it's fairly close. Basically 8's close to 10, so I'm just going to slide over. So now if we look at it, this is much closer to what I expected. This is approximately plus or minus 0.3%. That seems a lot more likely. Again, this is really just a super rough estimation. Grab a calculator for that. All right, so is that too much error? Well, that's a lot smaller error than my first mistake, but 0.3% doesn't seem like a lot. Is that enough for the ball bearings for your jet engine you're trying to build? Well, here's the interesting thing is, I have no idea. I don't build jet engines. But the people that do build jet engines have a book that tells you exactly how much tolerance you're allowed to have, how much area you're allowed to have. So when you go to this company and they give you the specs, you can say, okay, that's only about 0.3% error. That's within the realm that my engine will work in, and you could buy them from this company. If not, you'd have to say, nope, your machine's not accurate enough, I need to go find somewhere else. All right, that was a Calc 1 problem. Let's take a look at the only real difference that expands when we go to multiple dimensions here. So let's say, same idea. That's not even close to the word I was trying to write. Let's say we want a box that measures 2 by 3 by 10. The machine that makes the box has an error of, let's say, plus or minus 0.1 foot in the length and width, but plus or minus 0.5 feet in the height. What is the final volume? All right, let's do kind of the same question. I'm changing our shape here. We're now going to talk about a box. So we want a box, and we say we want the measurement to be 2 feet by 3 feet by 10 feet. So we want the volume of this box to be 60 feet cubed. But when we go to the company, they say, okay, well, to make this box, the length and the width we can get within a 1/10 of a foot, but unfortunately the height is going to be off by as much as a 1/2 of a foot. Now, does this seem reasonable? Again, you say, well, it's a machine, wouldn't it have the same tolerances everywhere? Well, if these sides are being cut by one machine that can only cut a maximum length of 4 feet, and they got to go to a completely different machine to cut this one, it might have a different tolerance. So different tolerances and different things could possibly happen. So if we wanted to do this, how can we find it? Well, first off, the volume of our box is length times width times height. Now, each one of these has a possible change in error, so we want for the differential for this. So a small change in volume would be, and we got to take the differential of this, which means we're going to have to take the derivative with respect to length, width, and height, and then multiply by the derivative in that direction. So basically what we're doing V sub L dL plus V sub W dW, V sub H dH. Okay, so we got to take the derivative of each one of these in each direction, right? In each direction that can move, and then multiply by its differential. So the possible change in volume would be the derivative of this with respect to L is just WH dL. The derivative of this with respect to W is LH dW, and the derivative of this with respect to W is LW dH. All right, so we just took the derivative with respect to each variable and then multiplied by its derivative. So, what is the maximum possible? Well, the width and the height, remember, just those you, the convention when we write a dimension is always length by width by height. The width and the height should be 3, 10, and DL. The maximum possible error and the length and width is plus or minus 0.1. Plus the length and the height, so that's 2 and 10. And the width also has a possible error of a tenth. And the length and the width were 2 and 3, but that has a possible error of 0.5. Okay, looking at all these, let's go ahead and say dV would be, that's 30, so it's plus or minus 3. That's 20, so plus or minus 2. 6, half of 6 would be 3. Now again, we got all these pluses or minuses here, so we're just going to group them the best way possible. So either they're all plus or they're all minuses, and we end up with 6, 8. So the possible change in volume, I think I said feet here, are plus or minus 8 cubic feet. So quite a bit. That would really change the volume of the box. 8 cubic feet seems to be fairly large, but let's compare it to what it should be. So the relative error, I'm going to stick this right here. In this case would be dV over V. This would be plus or minus 8 over the actual volume, again, supposed to be 60. All right, so dV over V would be plus or minus, let's see, 4 will go into both of those and give me 2/15. We can leave it kind of like that. So 2/15. That's less than a tenth off. Not that big of an error, but not that great either. Not that great at all. Now, is this enough? I don't know. I mean, is this within what we'd want? I don't know. So this is the type of thing, if you were building this box, you would need to know what the parameters of your box needed to be, and if that's close enough to make it work. So generally when we're looking at differentials to apply to how much error is in a problem, we look at the relative error instead of just the total error that could be created. Now again, remember when you're doing this as an engineer, that's plus or minus 8 cubic feet. This could be exact. This could end up being exactly 60 cubic feet and you get exactly what you want. But you always got to look at the worst case scenario just to determine, is it going to work if everything goes wrong?